All right, so today we're doing Leetcode 394, decode string. So this function takes one input. We're using JavaScript here, or TypeScript. Takes one input string and outputs another string. So some example. Let me change that angle. Some example inputs are, 3A, 3 bracket A, 2BC gets output like this. So essentially, any phrase inside of the brackets, you repeat the number of times of the number that's outside of the brackets. And this relationship can be nested as well. So this right here gets changed into, ACC repeated 3 times. So, looking at this intuitively, we're probably going to use recursion. Or that's the way we're going to solve this. So we're going to use recursion, though there are other ways to solve it. And essentially, we're going to kind of parse this string. When we find a bracket section, we will, when we find that inner bracket section, like at the end of our recursive tree, we'll take that string and then we'll repeat it by the number of times, by the number out here, and so on and so on. But obviously, to do this recursion, there's going to be base cases. So let's take our first base case, just an empty string. We're using single quote marks to save time. Empty strings is going to return an empty string. The phrase doesn't have any brackets. If it's, just like AB, we're simply going to return AB. We'll just simplify this up here. If it's just a number phrase, like a number with, phrases inside, repeat that logic. The problem says that anytime there is a number, any phrase will be well formatted, meaning anytime there is a number, it will be accompanied with brackets. So really the way I see to look about this is you find the first phrase, the first full phrase, with a phrase meaning something, like a number phrase, where there's a number in the brackets with another phrase inside, or just a letter phrase. So essentially, you find the first phrase, you decode it, and then you just return the decode string, aka recursive call, on the rest of the entire string. Make a recursion call. Like right here, we would, decode this according to logic right here, and then simply just call decode string on the remainder part of the string. So even if you have something really long, like, AB, 4, 5, Q, 6, A, some crazy string like that, you can just call decode string on the rest. So we're gonna write out our base cases here. So if s.length is equal to 0, we'll just return s. Now we need to check, does it start with a letter, does it start with a number? So we're gonna say, you know, if is letter well, we actually need to get the first character. So we're gonna say let f, aka the first character, equal s dot character at 0. Let's say if is letter f, then we need to find all the letters. So we're gonna start, yeah, we're gonna try to get all of the letters. So we're essentially going to divide our string into 2 parts. There's going to be the start, which, you know, is the first, you know, set of letters we find, and then the end, which is the part we just call the recursive call on. So we're going to let start equal f. And we're going to start looping over the remaining letters until we reach a letter that's not a letter. Until we reach a character that's not a letter. So we can just say, you know, let character equal s dot char at I. And if we say if C is a letter, we're going to do start plus equals that letter. Otherwise, we're just going to break this loop. And whether the first letter is, the first character is a letter or a number or whatever, we're still going to call recurse on the end, at the end. So what we're going to do is create a temporary, or create a variable called result, or just res for short. And we're going to, once we found all of the start, we're going to, you know, let result equal start. You don't even need to call decode on this. We actually don't even need to create start. We could have just created the variable result. And we'll write some easy helper functions. So we're gonna write a function called, you know, isNumber, and that's gonna leverage the JavaScript includes array includes method. So we're just gonna say we can just use index of return if, you know, 0, 1, 2, 3, 4, 5. And this is, so C is a string. But we're seeing, like, if that string itself has, like, you know, the essence of a number, parenthesis, and then function is letter. We know from the problem definition that the input can really only be a letter, a lowercase letter, a number, or a bracket sign. So we can, return if, sorry, this shouldn't be included. This should be index of is, greater than -1. And is letter is going to be, if it's not a bracket, and if it's not a number. Anyway, so otherwise, if letter, if we're at the start of the string, the strings are always well formatted according to the definition, so we know that it is a number. It starts with a number. So we'll do else. Now we need to parse the number, and we actually don't need to loop through character to build the number. Rather, we can just, we know that every number must be followed by a bracket. So we know numbers can be between, I think it was 0 and 300. So you might have a number that's like 205, that's 3 characters long. So we just need to find the index of the start bracket. So let bracket equal s dot character at, what do we say, character at? No, index of and we can technically start searching from the first character. That doesn't really help. And now K, where K is like 3 or 4 or 5, whatever the number is. K is going to be, cast into number, the substring of um, 0 to bracket. And yeah, the way substring works is if you do, it's exclusive on the last element. So if it's like substring from 0 to 3, it's only going to return the 0 first and second elements. And then, so our goal, what we're trying to do right here, is we're trying to find the phrase inside of the brackets that we can repeat k times, that we can concatenate k times. So, what you think you could do is end bracket is equal to s dot index of this, starting from bracket plus 1. But that's actually not going to work because some strings might be formatted like this, meaning if we encounter this bracket right here, and then we find the index of the first end bracket, it's going to return this index right here and not this one. So we need to keep track of how many open brackets we've encountered and not, return the index of finding the end bracket unless we found the end bracket corresponding with that one. So we're going to make another function called, another helper function called get end bracket index. And it's going to be we're just gonna keep track of the number of groups we have open, the number of parentheses groups or bracket groups. So we're gonna say, you know, let open groups equal 1. So this is gonna be the index of the start bracket. So while something, we're going to loop through one character at a time, you know, C is equal to s dot car at I if, you know, C equals another open bracket. We're going to say open groups plus plus. Otherwise, if C is a closed bracket, do open groups minus minus. Otherwise, do nothing, just go into the next part of the loop. And if open groups ever reaches 0, that means we found the ending bracket, meaning we should return the index we're at. And I'm gonna let I equal start bracket wow, yeah, sorry for cutting that off. I equal start bracket plus 1. And while I guess just while I is less than string.length. And you know, the problem says every string is well formatted, but if we ever got to the end of the while loop, we would return, you know, throw new error end bracket not found. So yeah, we can't have this call right here. It's really going to be get end bracket s, starting at where we found the bracket before. Okay, so now now we can call decode string on the substring between the two brackets. ds dot substring from right after the start bracket to right up to the end bracket. Well, really the character before the end bracket. And we are going to append decoded phrase to result, you know, k times. The result is empty right now. And yeah, we're gonna simplify our is letter logic. I'm just gonna say, you know, oh yeah. No, we'll keep that. No, there's some way to simplify that. Save a line or two of code, doesn't really matter. Anyway, so we now need to append to result of decode string of the remaining part of the string, you know, like the second section. So that's gonna be s dot substring interesting. Well, we can't do it in the common area. We have to do it in each individual if statement. So really it's going to be res plus equals decode string s dot substring. It should be end bracket plus 1. And over here, gonna be decode string. Where we at I? It's gonna be whatever the value of I is, or I plus 1. And then down here, we can return result. I mean, really, we could have just returned result inside of each of those if statements. All right, so let's check our work. We have, 3 base cases. One is empty string, one is letters, one is the number formula. First base case, we just return, S. Second one, well, and then we got to figure out which character everything starts with. So, if f is equal to s dot car at 0, if is letter, first character is a letter, we're going to loop through and keep appending to start remaining letters if they are letters. Otherwise, we will stop, record that value of I, and then I'm going to call decode string on the remaining part. If s is, a number, we're going to find the index of the first bracket, and we are going to get k, which is going to be the substring from 0 to right before the first bracket. We're going to get the end bracket. The way we did that was by looping, starting at the first bracket, counting the number of groups there are. We increase the number of groups when we find a group opener, aka a bracket. Otherwise, we decrement. Once open groups equals 0, we return that index we're at. So now we get the end bracket index. Decoded phrase is going to be, substring between those two phrases. We're going to call decode on it. We need to append, concatenate decode phrase k times, add that, and then add to that the remainder part of the string, kind of like we did here, and you return result. So the question is, what is the runtime of this? And you know, recursively, we're going to call our function, you know, at most n times. Depends on how many of these k numbers we have. But really so that would say, you know, upper bound n if each function call, each stack frame call only took constant time, but it's actually not going to take constant time. The thing that takes on constant time is the thing that takes the most time, as a complexity speaking, is this concatenate. Concatenation apparently it's linear proportional to the number of characters you are concatenating overall, which in this case is going to be k times the length of decoded phrase. We're going to say decoded phrase can be upper bound by n. You know, it's never going to be longer than the length of s, which we'll call n. So we're going to say that this line right here is going to take kn times. Well, the thing is, if this line is called by another line, and take another kn times, except this time n is kn length. And actually each k value is going to be different from each other. Like this k is different from this k, which is different from this, which is this. So you could say that, you know, on the very inner loop, we have the concatenation time upper bound by kn. And then on the parent loop of that, you know, the parent stack frame, the calling stack frame, we would have, you know, k2 times the length of this string, which is k1, kn, and then that, so on and so on. Well, that should be k1. You can look at this and kind of conclude that this little phrase right here is going to be less than whatever the maximum of the k values is. To the fourth power. And, if there were 5 k's, it would really be upper bound by max k to the number of k's, count k, power. And since this right here is going to be upper bound by max k to the count k minus 1, we can just ignore that, because like n cubed is always, or k cubed is always less than k to the 4th. So really the only term that matters is this right here. And now you could say, well, the number of k's is never going to exceed the length of the string. So you could simplify this to be that, but that's actually kind of misleading. The runtime complexity really does depend on count k and not n. Like, yes, count k is always less than n, but it can be far less than n. Like, let's say we have some big string where the length of n is 100. I'm not sure what the problem said. I think it said that the length of s is always less than or equal to 30. But so I know you could have n be 30, you could only have 2 of those be k's, and the maximum k could be 100. And so you could have 100 squared, times 30. Or you could have, you could have 100 squared times 30. Or I guess max k, you could say it's 2. So you could have 2 squared times n. So you could have this be 4n. But, you know, if they, you know, because count k could be 2, the result could be 4n. But let's say you were saying instead of count k, this value right here was n. Well, then you could end up having, you know, 2 to the n times n. And that's just totally different complexity class. So the time complexity of this really does vary based on what count k is, and count k isn't necessarily, count k can vary pretty differently from n. So that's the time complexity. Space complexity. Similar thing, you can say there's going to be n stack calls. So if we took, I guess to make this more clear, time complexity is upper bound by, you know, max k to the count k times n. At least the way I see it. I think Leetcode actually made this a little different, so I'm not totally sure. My recursive answer is different from Leetcode's. I haven't looked at Leetcode's fully yet. Anyway, space complexity. There's going to be n stack frame calls. So if each stack frame took constant amount of memory, you know, it would be order of n. But again, each stack frame is not going to be constant amount of memory. Each stack frame is going to have to store the result of the decoded phrase, which we just determined is going to be of length kn. So you might think, all right, it's going to be like kn times n, because we're going to have kn on each, you know, stack frame. And that'd be kn squared. Quadratic memory, that's not ideal. That's not going to happen though, because the result variable of the decoded phrase doesn't get initialized until after until after the recursive call for that portion of the string. You might think, oh, well, there's 2 decode string calls. The memory, I don't know, might end up using more than. So I guess what I was just saying is that the calling stack frame will essentially have its memory, you know, freed up right when, you know, the result gets returned, you know, into decoded phrase. So sort of like the memory allocated of that phrase just moves from one stack frame to another, and it doesn't duplicate itself. Well, you might think, oh, there's like 2 decode string phrases open. Maybe that makes the memory more than kn. Well, not really. Like, if you have 2 decode string calls, you know, like one from the start, one from the end section, this, I don't know, let's say this is just some big number kn. Well, this is going to be some other number smaller than kn. This is going to be some fraction of kn. And this too is going to be some other fraction of kn, where f1 plus f2 is equal 1. So I mean the split recursive calls is still never going to add up to more memory than kn total, like total, in all the current references out there storing the total length of result. So overall, we're just never going to have more memory used than kn. Now, I think we do actually have to modify this more, because the final string isn't going to be, you know, just any kn. It's going to be, you know, length 3 times 4 times 5